Tonight, really pleased to introduce Peter Lehman and Jana Ganion. Both are leaders in renewable energy here in the region, as well as in the state and nationwide. Peter has been involved in renewable energy since the 70s and founded essentially and designed the renewable energy or the clean energy portion of the environmental resources engineering program here in Humboldt State, and also founded the Schatz Energy Research Center jointly with Charles Chamberlain in 1989, and so has been at the forefront of renewable energy in our region for a number of decades. So really great to have him speaking. Jana is the Sustainability Director for the Blue Lake Rancheria tribe, but that title probably only covers about 30% of what she does. And a very large portion of it, for the purposes of this talk, is associated with developing clean energy projects in the context of the Blue Lake Rancheria tribe. But she's also involved in at both the state level and national level in energy policy related efforts in the context of Native American tribes. And he's a leader not just in our region, but in that wider context as well. So I will turn it over to the two of them, but great to have both of them here tonight. Please give them a warm welcome.
Well, thanks, Arnie, and hello, everyone. This is a very cozy group, so I want to encourage you to ask questions as we go along in the presentation. And if this becomes a discussion, all the better. So we're going to start with telling you what a microgrid is and why install one. And we'll talk about the microgrid that we just installed at the Blue Lake Rancheria and how it works. We'll talk about the group of partners that we got together for this project, and it was a wonderful group of partners. And without all of them cooperating, this wouldn't have happened. We'll talk about the commissioning, which took place on a very short time scale for this kind of project and forced us to be really efficient in how we did it. We'll talk about how it works in its first year of operation. We'll talk about how much money it saved and what other benefits it brought to the community. And then we'll talk about how this is progressing in our community. There are now two more, one starting to happen and one that will happen soon to benefit our local community. There you go. No.
So I'll take this one. How many of you here are not terribly familiar with microgrids? All right, a few. So, we just wanted to take a couple minutes to say a microgrid is basically, the one that we built at the Blue Lake Rancheria anyway, is a mini electrical grid. That in our case, and there's many flavors of microgrids, which we'll talk about a little bit later, but in our case, it can disconnect from the PG&E infrastructure and reconnect with PG&E in planned and unplanned scenarios. So we can disconnect, use our own power that we generate on site to power our own facilities, and then during connected mode, we can use our on-site generators, specifically the solar array and the batteries, to offset some of our energy use and to make the grid more resilient. A microgrid consists of these things generally. So we talked about generation sources. At the Blue Lake Rancheria, we have the solar array, which is about 0.5 megawatt. It's about 2 acres and 1,536 panels, I think. So it's big. It's the biggest one in Humboldt County so far, although we are about to be eclipsed by upcoming projects, which of course we love, and that's one of the reasons we did it. Energy storage to make best use of that solar power. So we have a megawatt hour of Tesla batteries on site, for example. And then we'll get to the details of that in a minute. And then at the core of it is a smart control system that allows us to generate this power and place the power where we want it, when we want it, control how much power we use, make sure that that power is even throughout the system and controlled, and above all, make sure that that power is generated and used in a very safe manner, both within our system and as it relates to the PG&E wider grid. Can you turn this side for me? Thank you. So why do we do it? We did it for a number of reasons. The Blue Lake Rancheria, I'll speak from the Blue Lake Rancheria tribe perspective, and then I'll have Peter speak to the Schatz Lab perspective. The first bullet point is actually incredibly important. As I'm hoping everybody in this room is aware, we have to move really quickly. We have not a moment to lose to green our grid and generate our electrical power from renewable and zero carbon sources, ideally. And we have to do that at a faster pace than we're doing now. So that top bullet point is one of the reasons that we do this. The Blue Lake Rancheria tribal government has aggressive greenhouse gas reduction goals. We want to hit zero net GHGs by 2030, and we're well on the way to doing that with this project as a big part of that effort. Advances climate goals, as I mentioned, we have a significant problem to solve. Luckily, with the technologies that we have in our microgrid, we can solve that problem. So there is so much room for optimism today, especially because of the work I think that we're doing in the microgrid sector, and not insignificantly, solar plus battery storage. And I'll repeat that again, solar plus battery storage. It increases our resilience. So emergency power really creates this safety net for all of the lifeline sectors, which also include, on top of energy, water, food, transportation, and communication and IT infrastructure. So our ability to have emergency power in any situation is really key to providing resilience across all of those lifeline sectors, both in an emergency, but also as sort of an economic enabling investment to support economies and support jobs and support all the governmental and enterprise programs we do out at the Rancheria. And then it increases, hopefully, grid stability. So PG&E knows that if the power goes down and they don't have to come to the Blue Lake Rancheria first, that we're fine, and we're going to be fine for really as long as they need us to be. So that sort of helps the grid stability. There's other stabilizing technical aspects to this that we'll cover in a little bit. And then in a business as usual sense, it allows us to do some energy arbitrage. And we'll talk in detail about why that's important, both from an economic standpoint, but also from a power balancing standpoint. That sound good?
Thanks.
All right.
And I just want to point to a couple of things in these pictures. The person in the middle here standing next to Jana is Kristen Ledecky, who is at the Schatz Lab and participated in this project. And this is Randy Cox, who I'll mention a little later. Notice a 4-foot handle working on 12 kV. So we were working on high voltage.
12,000 volts in that little box.
So how many know what the duck curve is about here? Everybody knows about the duck curve? I'm going to explain the duck curve anyway. This is the original duck curve that the California Independent System Operator produced, I think, in 2013. And the issue is this. As we're getting more and more solar generation in the state, the load, which used to be extreme in the middle of the day, especially in the middle of the afternoon, is now becoming less and less. And there are actually times in California now where wholesale power is negatively priced. The independent system operator will pay you to use power. And then the sun goes down, people go home, turn their appliances on, and there's a huge upsurge in the net load. So the net load is the difference between what we use and what we generate. And that has been an issue for California. What do we do about that? It's really hard to regulate the power system when you have these large changes in a short time. And the answer is energy storage and electric vehicles. That's another form of energy storage. And they can flatten the duck curve. They can eat up the power during the times when it's plentiful, and they can deliver the power when we need it. And the control system at the Blue Lake Rancheria is designed to work the solar panels and the batteries so as to help out the duck curve. And to respond to financial incentives, the rates. Actually, the rates in California are still, the tariffs have not caught up with the reality of the duck curve, but they are getting there. Any comments, questions about that? Is this you? Yeah, I think it's you.
We're prone to disasters and disruptions, like this graph covering up the bullets. But why do it here? There's been a couple articles that I have to joke with Peter because he actually very kindly put together this whole presentation for us both, which I really am grateful for. And that's Greg Chapman explaining very patiently, it looks like, maybe what the duck curve is. So everyone probably knows this, so we'll just run this through quickly, but this is something that when I travel to other parts of the state or other parts of the country, and I'm talking either with state policymakers or national policymakers and other tribes and other cities and counties, that we need to reiterate to them because it's important. People don't understand how isolated we are geographically up here. They don't understand you have one power loop, like you have one line, what? You have one natural gas line? What are you talking about? So we do have a constrained energy basis up here. And so, and we obviously live in a disaster-prone area, especially with the earthquake and or tsunami risk, and of course the wildfire risk, which is considerable and getting worse. Also, you know, kind of another underpinning for solar or renewable energies that don't rely on fossil fuels is that diesel fuel up here is shipped in by barge or it's trucked in. And you guys remember the 2 landslides that happened at the same time?
You'll get that.
Oh, I'm going to get there.
Yeah.
Thank you. Never mind. Wait. So anyway, so we're subject to constrictions. And then, of course, out of the area of factors like hurricanes ripping through refineries and things would also impact us and has impacted us in the past.
And let me say that the idea that we could respond to an emergency was a big factor in our getting this award. That is what we stated to the California Energy Commission when we wrote our proposal, that this was one of the big advantages of installing this system. And obviously they thought so too. So here's your slide.
All right.
Go for it.
So this is, you know, these are some of the pictures that we all know here. That picture on the top, I'm so bad at this, your top right, is a wildfire that blew up in Blue Lake on October 8th last year. It was about 25 acres. Luckily, it didn't hurt anybody like the other wildfires have done. But it was an example of, even on the foggy, rainy, relatively cool, temperate coast, we're still subject to wildfire that can, you know, happen in an instant. So we obviously live in earthquake country, and any of you in the room haven't accessed Humboldt State University's Living on Shaky Ground, you should look at that website. It's great. It has a lot of resources. And that's a photo from that website. And then the landslides did constrict our diesel shipments when those two happened, were basically simultaneous. In 2017, they constricted our diesel shipments to our gas station by about 60% for over a week. So we have seen some of these impacts, obviously, here on the North Coast. And I'll just say, as a little bit of an aside, that in 2011, you guys remember the Fukushima earthquake and tsunami. There was a tidal wave rolling across the Pacific, and a lot of people from this area evacuated inland. And even though it wasn't a mandatory evacuation, it was a self-evacuation event, people acted with common sense. They're like, you know, we're just going to move inland until we know how bad this is, and then we're going to come back. And so within about an hour or two at the most of that news breaking, we had about 1,000 cars out at the Blue Lake Rancheria, and panicked people who were really afraid of what this event was going to be. And we were really overwhelmed. And this was in 2011. And so that event really propelled us to start thinking about resilience and emergency preparation in a different way. And of course, when we did think about it, we wanted to do it with the lowest carbon solutions possible. And so, as Peter mentioned, we serve as an American Red Cross shelter in times of need, so we're pre-certified. If Red Cross decides they need a shelter locally, they will come out to the Blue Lake Rancheria. And our Sapphire Palace building, which is that glorious white tent we have out there, will be taken over by the Red Cross as an emergency shelter.
And let me read the last line here, which this PC has screwed up from my Mac.
That's the problem.
No. The microgrid will keep critical power flowing in an emergency.
Yep. That's good. So was this me?
Yeah.
Yeah. Okay, so as I mentioned earlier, this is some of the main components. Right now, we have about, I say a half a megawatt. It's really 420 kilowatts AC of solar PV. As a non-technical person, I still don't quite know the difference between AC and DC. But that's what we have. It's about a 2-acre array. And the National Renewable Energy Laboratory says that if you're going to build a solar array, you need about 4 acres for every megawatt. And so we came in at about a half a megawatt with a little under 2 acres. So we're kind of proving up some of those national numbers too. We have a Tesla lithium-ion battery storage system that's 500 kilowatts of power and 950 kilowatt hours of storage. To give you a sense of what that means, at full strength, like let's just say New Year's Eve, with everything going, that battery could power our property for about 2 hours. So if that kind of makes sense to everybody. And then we had some, even though we don't like them, we had some pre-existing diesel generators on site. So we have one that's a megawatt in size, and we have one that's 80 kilowatts in size. Those were put in about 2000 or before. So they are legacy. We did not buy them new for this project. And one of the goals of the microgrid was to really migrate all of our backup power needs for just business as usual to solar and storage. So storage is a great sort of baseline uninterrupted power source for us. And so those batteries are really functioning well within that system. And hopefully, though, we'll keep the gensets as deep backup, like deep emergency. If the power's out for a month, we're going to use them because we're going to be providing services with them. But on a routine basis, we are actively moving to disconnect those from any kind of regular use. So the loads, it averages about a half a megawatt. Our peak is a little under a megawatt. That's if everything is turned on at the same time, our 2 elevators, all of our HVAC, we've got all this inrush currents all happening at the same time. That's about our peak. And it's a 6-building campus, which includes our government offices, the casino, the hotel, the restaurants, the event center, and then all the supporting infrastructure in that area. We do have automated load shedding, which we'll get to when we talk a little bit more of the technical detail. And then we also will talk a little bit about our seamless transitions when we talk a little bit more technically. The other piece that's not on here is that as a part of this project, we had to purchase our PG&E infrastructure. So all of the PG&E lines and equipment, transformers, et cetera, we purchased that from what's now a point of common connection all the way back to the end of the microgrid.
Right there. So
yeah.
On the diagram, there's one spot where the microgrid connects to PG&E, and on one side it's microgrid, the other side it's PG&E. On the side that it's microgrid, it all belongs to the Blue Lake Rancheria.
Let's go to the next slide because I think it's that plot plan.
Okay. I just want to say something about load shedding. It is a 2-hour battery at full load. In an emergency, we would dump a lot of loads. So the battery would last a lot longer. And in a true emergency, if we had to go for weeks, we would really get down to just the basic loads for life and safety. And then we could carry a lot of the load with the solar and battery, especially, we're going to mention, the battery's going to get bigger.
Yeah. So this is a top-down plot view. It's pretty straightforward. I just want to, all right, I'll use the laser, but I'll mess it up. I did it. All right, point of common connection is here. So all of the infrastructure down all the way around to here, we bought all the PG&E infrastructure. And luckily we were at the end of the line. So it's not like this continues on to some other power source down here. This was the end of this particular trunk line, so it was really easy to define what was included in that purchase and how we were going to purchase it. Well, it wasn't easy to do it, but there's a little funny story about that too that we'll talk about. But anyway, so this is the government office. These are our gen sets here. This is the megawatt and the small one. And then this is our big, beautiful solar array, and our battery system sits back here. And
push the button, you'll see.
What? Oh, yeah. And so this is obviously the solar array. The battery is this little white box here. So it's a very small footprint. It's very kind of elegant and nondescript and subtle. So the Sapphire Palace, it's a grandized name, is here. The casino hotel is here, and then the tribal office is here. And so this whole campus right in here is what we've included in our first phase of the microgrid. This is the wastewater treatment plant that belongs to the city of Blue Lake that was put there when the tribe was terminated, but we won't get into those details. All right, microgrid functions.
That's me.
Here you go.
So these are some of the things that the microgrid can do and needs to do to operate the way it does. First of all, it can disconnect and reconnect to PG&E at will for planned islanding. And that's at the point of common coupling. And in the future, if, let me step back. In the old days, a few years ago, BLR used to participate in demand response for the state. So when the state needed the rancheria to use less power, they would disconnect some of their circuits from the power lines and run on the diesel generator. Nowadays, in California, you cannot do demand response with a diesel generator. It's illegal. So you have to use a renewable source. So in the future, when their battery gets bigger, as we'll say in a little while, they can participate in demand response using solar energy and the battery. It has automatic islanding and reconnecting if PG&E goes out. And we'll show you there have been 4 outages, and there's a slide that shows them, since in the 1 year that the system has been running. And the system has worked really well. The outage occurred, and the system islanded, and everything continued happily ever after until PG&E comes back on again. once it is islanded, the microgrid controller has to balance the loads in generation. And that's a complex function that needs to be done, and so far this system has done that very well. The interesting thing is, you know, most of our power systems rely on rotating generators, and the inertia of the generator keeps the frequency constant in the grid, and that's a very important thing. But this system can run on the inverter only, so that when it's islanded, that means the generator is off. If there's enough energy in the battery and the PVs to support the load, we can run on just the inverter and the energy from the PVs, and electronics are used to keep the frequency constant and the voltage constant. And that's a new world for grid power, and this system does it well. There are controllable loads for load shedding. So in an event, if we need to disconnect certain loads, there's a sequence of events that occurs. And first of all, we can turn off the tribal office. Then we can turn, in a rotating fashion, turn off some of the HVAC, and then turn off some of the ventilation. And eventually we get down to the point where the only loads are the life and safety loads. There is energy arbitrage. Arbitrage is, I'm sure you all know this, but I'll say it anyway. Arbitrage is buy low, sell high. So with the battery and the controller, which has the rate structures built into it, it will look ahead to see how much solar energy it can expect and what the rates will be, and it will decide when to charge the battery and when to discharge the battery to make the most money and run the system optimally. And that's the Siemens microgrid controller that does that, and it does it really well. Yeah, okay. So one of the things that this system does as well, when you pay your electric bill and you're a big customer like BLR, a large fraction, and we'll show you exactly how much, a large fraction of your bill is not just the energy you use, but it's the power that you drew from the grid. So if you draw a certain amount of power for a short period of time, you're billed for that maximum amount of power that you drew that month. So it behooves you to shave the peak and keep it as low as possible within reason so that you can run all your loads. And again, the optimizer does that and sets a level and doesn't allow the peak to get too high and therefore decreases the bill. And you'll see that it really works. We'll show you the data. Let's see. Another thing we had to do was we had to tell PG&E how much power we wanted to export. And that was kind of a guess on our part, because if you export a lot of power, I mean, they're a net metered customer, so if the more power you export, the lower your bill. But if you export too much power, then PG&E is going to come back and tell you, you know what? You have to upgrade the grid downstream because we can't take that much power. So we had to make a reasonable guess at how much power we could export without touching off a PG&E, oh, you need to pay us more. And we guessed at 100 kW, which was probably fairly modest, but it worked. PG&E said that's fine. And so we cannot export more than 100 kW, and actually, we haven't exported any yet, right? Have we? Oh, well, for fractions of a time. Yeah, for small times. Another thing that we have to worry about, and we put in this, it's called, wait a minute, let's see, am I on? Okay, so there, there's also automatic curtailment. So assume you're in this situation. The solar is going gangbusters, the sun is out strong, and the battery is fully charged, and you're now producing more power than you can use. What do? You can't export it beyond a certain amount, so you have to curtail the PV. So that's another thing that the microgrid management system does. Here's another situation that might happen. That is, it's a partly cloudy day. The sun is behind a cloud, and all of a sudden, the sun isn't behind a cloud. And the PV power goes from very little to a lot. And that plays havoc with the power management. So the microgrid management system allows us to increase the PV power only in small steps so that you don't get this sudden increase in power. We saw that in our first solar hydrogen project. Remember that? We saw incredible shifts in solar energy around here when there's a day with puffy white clouds. It's pretty impressive. There is a manual lockout of the breakers. If somebody is working on a high voltage system, you want to make sure that it doesn't go live. So there's a lockout function. And as Jana was saying, the diesel generators now, especially if we increase the battery size in the future, will be relegated to not running very much at all. Hopefully not at all. Oh, all right. Oh, yeah, I do. Actually, go back one more. Okay. Thanks. There are 3 people shown on these 2 photos. Mark made both photos. Mark Marshall and Randy Cox. Mark works at the Schatz lab, and Randy was the head electrician on this project. And there's Dave Carter and Mark Marshall in a situation they were in for about 1,000 hours during this project, sitting together looking at computers going, oh, I don't know. Dave was the main cat herder for this project, and Mark did a lot of the programming, and Randy Cox was a wonderful electrician. The 3 of them really are responsible for the success. I mean, a lot of people are, but they work their butts off and are really responsible for the success of the project. All right, onward.
So that's a great segue into this slide. We're going to spend some time on this slide, so settle in. One of the key benefits of doing a project like this, and one of the most essential components of it, are our partnerships. And so when I talk about this project, both across the state and nationally, what I really want to impress upon those audience that don't know anything about this area, they don't know anything about how we did what we did, is to say, you know, if you look at this, this is really an example of a public-private partnership, academic industry, government partnership, all of those sort of partnership terms of art that the government, especially on the federal level, like to throw around. We have demonstrated the success of those models on this project. Of course, we were fortunate to be working with expert partners. So I'm going to go through each one of these and talk a little bit about what everybody brought to the project itself. So I'm going to start just with this on the far right there with the State of California Energy Commission. So the California Energy Commission has a program called the Electric Program Investment Charge. It is a ratepayer program. They contributed $5 million to this project. They were the primary funder. The total project cost was about $6.3 million or so, which is a really good value, by the way. But they were the ones through that EPIC program that they fund projects like this. They fund leading edge projects that have among its goals and objectives and technologies, things that they want to prove up. And the only way they're going to prove it up and see how it's implemented and what really happens and what are the economics and what are the technological barriers and what are the lessons we've learned and what people do you need on the project and what resources is to do the projects. And so we've been really fortunate to have sort of a dream team here that the tribe has been fortunate to be part of for some of them, but then they're also happening all over the region and in other combinations. So the California Energy Commission is our primary funder. They oversaw the project from their perspective, and we did collaborate with them very closely and very well, and they were extraordinary to work with. I'll knock on wood. I mean, they were just low maintenance. You know, they were really accepting of our project schedule that stayed pretty close to what we had promised, but still, you know, there's always those things that come up. They were great to work with. So if you have any questions about that, we'll leave that there for now. I get to talk about the Schatz Energy Research Center because none of the projects that the tribe has undertaken in the energy realm or really most of our sustainability work would be possible without the Schatz Energy Research Center, Humboldt State University, and the students, staff, and faculty that are here. It has made all the difference. And the Schatz Energy Research Center, our relationship began, I believe, when Peter Lehman said, you know, I have this crazy idea. And we said, really? What you got? So the Schatz Energy Research Center, it was obviously the prime contractor with the CEC on this project, but as Peter said, Dave Carter, Mark Marshall, Jim Zolik, Allison Hansberry, the whole Schatz Energy Research Center team really did an extraordinary, there's actually not enough superlatives to talk about it. They were unfailingly expert and professional and the hardest workers and the greatest attention to detail of any project I have ever been involved in, and it was a true joy to work on this project. In addition to being the prime with the California Energy Commission, they were also the system integrator. And so for microgrids, just as as another thing that you probably already know, the system integration is possibly the most difficult and the most, in the end, rewarding piece of a project like this. And Dave Carter and Mark Marshall, did everything. They identified those gaps between the manufacturer's technology. They identified where manufacturers were missing the whole concept of working together on a microgrid, and they filled in all of those gaps and they made the system work as an integrated system. And one of the first things that we tell anybody that wants to create another microgrid is that you have to have a knowledgeable, expert system integrator. And that's the primary reason, I think, out of everything for this system's success. Pacific Gas and Electric, well, I'll leave that there for now, although I could talk for an hour on that. Pacific Gas and Electric, big investor-owned utility. They're obviously, they have different things that they're responsible for, and they have big, huge areas of responsibility that are outside of our region. But I will say that even though microgrids, when we started this in 2015, were firmly outside their business model, they rose to the occasion. They provided the support that allowed us to get the funding from the California Energy Commission. It was a requirement to have your utility on board to get the funding. And they worked with us throughout the project, value engineering, safety engineering, making sure that we had what we needed, making sure that our paperwork and our documentation, we signed 4 different agreements with PG&E during the course of this project, making sure that was all correct. They've just been stellar. The tribal government, I will just say that this project is a result of their vision for the future. They want a low carbon future where energy costs are levelized and controlled and are green. And so I'll leave that there for now because we're running. We gotta move if we want to have a discussion. Siemens, big, huge international company. They do everything from wind turbines to microgrid controllers, which they did for us. Their microgrid or their systems controls powers like the Eastern Seaboard. This was their first project where they scaled all that down into a community effort, and it's worked very well. But again, largely with the stewardship of the Schatz Center. Idaho National Laboratory, they were the ones that brought the project to us in the first place. Rob Hope-Sapien, one of their leaders there, knew.
Yeah.
I'll let you tell the story.
I knew Rob 20 years ago when he bought some student fuel. So he was a professor at Florida State University, and he bought some student fuel cells from us. And he's been a friend ever since. And they had a project with Siemens on the East Coast to build a microgrid, and it fell apart. And then he saw this California funding opportunity, and he thought, California, the Schatz Lab, I think I'll call them. And that's how this all started.
We have Rob to thank for that. And Idaho National Labs, they did hardware in the loop testing. So without going into detail, we recreated the microgrid in their lab and then tried to break it before we brought it on site and did it live here. And in addition to finding a bunch of bugs and fixing them there, it allowed us to send our staff to INL to do training on a system that wasn't live. So they put the system through its paces, they learned what it did, and then they were, in great shape, or at least much better shape than they would have been otherwise when we brought the system on site and installed it. GHD was our electrical engineering firm on the project. Again, big international company, lots of deep expertise. They were great to work with. Tesla, we've talked about the batteries. They were extraordinary in terms of engineering support. This is the first battery system that they've deployed as a part of a microgrid. And without going into detail, that is complicated. They had to work through a lot of things. And again, with Dave and Mark shepherding this whole process, they really, though, rose to the occasion and helped us through a lot of really challenging, just integration issues. And so now it works beautifully, and as Peter said, we're going to expand that to double our battery size this year. REC Solar was our solar contractor. They did great work, but I have to say that we need to give a nod to McKeever Energy and Electric here. McKeever was their subcontractor, and they actually did most of the work. And if you look at our solar panels, they're extremely straight. They're just lovely. Kernan Construction is our longtime civil contractor. They did all the grading and grubbing, and again, our solar array is beautifully straight. They did a great job for us, going above and beyond, as they always do, their original scope of work. And then last but not least, certainly not least, is Robert Colburn Electric. In the ground war on climate change, you need a good electrician, in addition to your engineers. Randy Cox from Colburn Electric has done work for the tribe for about 20 years now. He knows every inch of wire on that reservation, and he has this lovely Tennessee lilt to his voice. He's wonderful to work with. He always rolls up his sleeves. He problem solves, and he's provided a lot of design, deployment, and commissioning insight to us from a field level, just because he's experienced and he has worked on big and small power plants across the country that we wouldn't have had otherwise, and we probably would have thought twice about doing the project had we not had his expertise in our corner. So it's great. And then I will just give a nod to our on-site staff at the Blue Lake Rancheria before I hand it over to Peter to go through commissioning, and it's 6:20. So the staff at the Blue Lake Rancheria, especially our facilities staff and our IT staff, this was new to them. I'm the one that was the project manager, and it's sort of, they had input in at the front, but they really had a lot of things kind of dropped on them, and they rose to the occasion, and we all pulled together and did a really good job. So proud of that.
Okay, so I mentioned earlier that, excuse me, that the timeline was short for this project. It was extremely tight. And kudos to the team that brought this off. So we didn't start until October 2015. That's the kickoff meeting. The guy on the left is the Siemens engineer, Shashank, who we've worked with. And the guy in the middle is Rick Gugiana from GHD. He was the electrical engineer. We got to 50% design review. Notice that's a very short time. And we had 90% design review by May, so that we could start, back to that, we could start early construction as early as May, so that we would be on schedule. And next one. And then the design was complete in September, so less than a year after we started. That's the installation of the batteries. We had to pass a pre-energization test with PG&E before they let us turn anything on. And then we had the cutover to primary service. So we've mentioned this. Originally, the Blue Lake Rancheria was a regular energy customer. And they had 3 different accounts that were owned by PG&E. The wires were owned by PG&E. The transformers were owned by PG&E. As Jana said, they bought all that, and all of a sudden they were running a 12 kV line, a 12,000 volt line, and this was the cutover to the 12,000 volt service for the Rancheria. And then, as Jana mentioned, we used Idaho National Lab to test the software and to do operator training and de-risk things so we could all make our mistakes on a simulator. So our TDS is a real-time digital simulator. So we could simulate, and some of it was actual hardware, was hardware in the loop, but some of the components were simulated by computer. But the whole system was put together, and then we could put it through its paces and see what worked and what didn't. And the operators, as Jana mentioned, could push buttons and see what happened. And so that took place in January. So we're now last year, January of last year. And then the final PG&E inspection is the pre-parallel inspection, which we passed except for seamless transitions, which we'll talk about in a minute. But they were so impressed with our system that they gave us a tentative or a provisional permission to operate. And then we fixed all the bugs. And in July of last year, we got final permission to operate from PG&E. And you know, PG&E, to their credit, is very persnickety about what goes on their grid. And they should be. And, you know, we got there. Yeah. So I mentioned earlier there were 4 islanding events. They happened in October, December, and this March. And you can see the length of time that each event lasted. Everything worked perfectly. Within seconds, the power switch, the microgrid disconnected from the grid, and power was reestablished using the internal power sources in the microgrid. And in fact, in most of these cases, all of these cases, nobody even realized, right? Yeah. So the islanding happened. No one realized that it did. The system worked well. It waits for 15 minutes. If the grid is steady for 15 minutes, then it reconnects. And so it's working. Okay, a couple of graphs. Here, I need the pointer. I can't do a presentation without a few graphs. So this is the PV array performance in the first year. And the red line here is, and thanks to Charles for this graph, the Schatz Lab is blessed with Dr. Data, who produces wonderful graphs. the red line is the actual production month by month. This is megawatt hours per month by month of the PV array. The dashed line is correcting that for a typical meteorological year, because the original production or the original prediction of the solar performance is based on a TMY, a typical meteorological year. And that's over a number of years what the average solar energy would be in that year. And of course, every year isn't the average year. So there were some months where the insolation, the sun power, was larger than in a TMY. In some cases, it was less. So the dashed line, there we go. The dashed line corrects for those differences. Then, the reason there are glitches there is there were glitches in the system. There were times when things didn't work. There were times when there was a lack of communication between the microgrid management system and the array. So the array was shut off. So we lost power. If you assume that the array worked all the time during that time, then it would have produced this green amount of solar energy, and the blue amount of solar energy is what REC Solar predicted we would get. So it's an amazing, they agree with each other amazingly closely. There you go. That let's see, the blue line is what they told us, and the green line is what it would have been had there been no curtailments. So the PV array works just the way we imagined it would, which is not that surprising. We're pretty good at predicting PV array performance these days. Okay. Okay, I talked about a seamless transition. If the battery and the PV array have enough power to supply the whole load, and you're doing a planned islanding event, you can do it seamlessly. So the other times that the microgrid took over when there was an unplanned outage, that was a so-called break before make. So it disconnected and then it reconnected the microgrid. In this case, if it's a planned transition, it can connect in a matter of a fraction of a second. So there's almost no interruption in power. If you were looking carefully at a light, you might see it flicker. It's almost like this huge Tesla battery is acting like a UPS, an uninterruptible power supply. And Tesla is getting better and better at doing this, so eventually their battery systems will be UPSs, and they will act seamlessly. And this is a test that we did, and so this is the load, and actually see what we did was the battery isn't very big, as we've said before. We decreased the load by turning things off and locking out the elevators, because when the elevators start, there's a huge surge of power. And we got it down to a low value, and then we did a seamless. So this is on grid power, then it's on microgrid for 8 minutes, and then it's back on regular grid power. And pretty amazing. It works. Let's see. Where are we? Here, that's you.
Oh, okay.
You're the money girl.
One of the reasons that the tribe did this, as I mentioned at the top, was that they're looking for ways to reduce and levelize their costs, to have predictable energy costs over time. And so this is some of the initial results from the microgrid. We've saved about $150,000, which again is during a commissioning period. We essentially are still kind of in a final commissioning period and kind of tweaking some things. So we expect, again, that to increase to a couple $100,000 a year in steady state. But it's interesting to see a couple details here. 91,000 or 61% of that is due to the microgrid operation, and 39% is due to the switch to primary service. So what that means is that you pay less for your power when you switch from secondary to primary service with PG&E. You become a wholesale power purchaser, basically, in other words, or from Community Choice Energy now. But the majority of the savings is due to microgrid function, the importing of solar power, the battery, the use of the battery and the arbitrage. And then within that 91,000, 57% come from direct energy savings and 43% come from that peak shaving that Peter was talking about earlier. So it really pays, literally, to pay attention to peak shaving, and we're excited that the system will do that seamlessly for us and without us having to watch a 15-minute price point on power or anything like that. So I'm going to just briefly talk about benefits really quickly because we've touched on some of these. To me, the third bullet is something that we haven't really talked about. We've been able to use the savings from the microgrid to add some jobs at the tribal government, on the tribal government side. We've added 4 permanent jobs, which I refer to as a 10% increase because it sounds better. But it leads to an interesting point, which is when we first started this microgrid project, we thought that the people that were going to manage it, once we hit true operation and maintenance mode, were going to be our facilities people because it's a power system, right? And it's mechanical. What we found very quickly as we got into this is that the microgrid, the MGMS, the microgrid control system, the sub-control systems really requires a partnership between facilities and IT. And so this is another recommendation we make out to people who are considering putting in a microgrid, that it's not just about facilities anymore, or your facilities department is going to need some IT-related skills and confidence to be able to operate a system like this, for the lifetime, which hopefully is several decades. So we're pleased about the job creation. We've added a couple of jobs in facilities, and we've had a couple of jobs in IT, and those jobs wouldn't have been created without this project. We've talked a little bit about public safety, but just to reiterate that that's really important to us. And then, of course, we have the project itself. And projects like these obviously bring in resources from outside the area, like the companies and our partners that we work with, like the $5 million from the California Energy Commission. We bring all of these resources into the area that we wouldn't otherwise have. And using a very conservative multiplier, we have achieved about, the cost of the project was about $6.3 million, but in addition to that, we've achieved about $10 million of induced and direct economic benefit throughout the region. And that's, created and maintained jobs in other companies, in our contract area, administration. All of these things tend to work together, and so gaining more of a reputation for doing these successful projects will lead to more outside resources coming into our area, and that's important to keep in mind. And then market development. So one of the things that I like best about this project is that because it's CEC funded, we make the stuff that's not proprietary IP, but we make all of the project information public, so that other people who are looking to develop microgrids can see what we've done, can look at our lessons learned, can look at all the innovation that Jim and Dave and Mark and Allison and everybody on the team really created as a part of this project, so that they can do their own projects. And again, the goal is not awards. The goal is to implement renewable energy, green the grid as fast as possible with these kinds of systems. So we've been fortunate to receive some recognition, some well-deserved recognition, particularly for the technology and the engineering. And these are some of those. We're going to zip through them because they make me embarrassed. But then, obviously, it's led to other projects really quickly. April 19th, between 11:30 and 2 o'clock, I'd like to invite you all out to the Blue Lake Rancheria. We are doing a groundbreaking ceremony for our latest microgrid, which is another partially CEC-funded project. It's going to be at the gas station and convenience store, and we're going to put a nice big 60 kilowatt array on top of that canopy. And we're going to have a Tesla battery in the back, and we're going to have advanced building controls that tie it all together, so it's our mini microgrid or our microgrid, which will be extraordinary. And one of the reasons we're doing it is because there are 12,000 such stores across California, and the CEC is funding it so that we can put together a package, a microgrid package, for these kinds of stores, which, especially in rural areas, are critical infrastructure and do provide, both in business as usual and emergency situations, critical services to the local population. And then I will hand it over to Peter to talk about ACV, and then I think we might be...
Yeah, we're just about done. So we're also doubling the battery size. So Jana didn't say that we've gotten a self-generation incentive program award. So the battery is going to double this summer, which is going to make the system even more robust and more able to handle the load in an emergency. And then, come on. This is a project that just happened, and some of you read about it. We just received a $5 million CEC grant, another one to build our third renewable microgrid. This one's going to be at the airport. And RCEA, the Redwood Coast Energy Authority, was a wonderful partner, and they put up $6 million in matching funds. It fits with their goal of developing local renewable energy. This will be the biggest array in Humboldt County, almost 5 times as big as the array that's out at Blue Lake. It will cover 7 acres, to give you an idea. It's a pretty big array. I mean, for Humboldt County it is. An 8 megawatt hour battery, again, a Tesla battery. So 8 megawatt hours is like 100 Model S cars. And this will keep the airport and the Coast Guard Air Station energized under almost any conditions, because it's such a large system compared to their load. Well, actually, I can't, because it's going to be right here. Yeah, it's going to be on the road. You go to the airport from the south. It's going to be along that road. It's going to be south of the runway. And I just want to say this is going to be a very interesting project. PG&E has been wonderful in helping us get this together. It will be the first multi-customer microgrid in their service territory. So it'll have 18 separate accounts. It's different than the situation at Blue Lake, where the Rancheria owns the whole microgrid. This isn't true here. PG&E will own the infrastructure. RCA will own the battery, the generation, the PV array, and the battery. It will bring up all kinds of interesting issues that we're going to have to deal with, like who pays for the power during an islanding event. It's being produced by RCA, but it's being delivered by PG&E. Is there a tariff for that? There isn't. And we're probably going to have an experimental tariff. Another point is the customers here are getting increased reliability and resilience. Who pays for that? And how do they pay for it? And all these things are going to have to be worked out eventually, probably by the Public Utilities Commission in California. Yeah. Well, it's just, that's life. That is, most microgrids in the future will be multi-customer microgrids. It's not an advantage, it's just a fact of life that there are many customers on this microgrid. This one is similar to the one in Blue Lake because it's the end of the line. So this line goes out to the airport, and that's the end of the line. But there are 18 clients on that line that, and the wires and the transformers are owned by PG&E and will continue to be owned by PG&E, whereas that wasn't true in the Rancheria case. And then, you know, in the future, they're going to be microgrids that are in the middle of a transmission line and are going to have hundreds of customers. And we're going to have to work all those things out.
One of the key differences between the rationale for funding our microgrid was really a demonstration project. Prove it up. This one is going a step further and saying, you know, expand the scope, but also prove the economics. So just to add to what Peter said, you know, when you have community choice energy and our CEA involved and you have PG&E involved, they're the ones that are going to have the ability and the responsibility across their regions and their spheres of influence to implement these. They're also going to be able to implement these a lot faster than you can on kind of a one-off basis. So by getting, you know, a community choice aggregation, the community choice energy group involved, and by getting the big IOU involved, investor-owned utility involved, you have the ability to scale. But they need to figure out the economics, and that's what one of the points of this is, in addition to critical infrastructure. So this funding was for airports, military bases, and we're lucky here that we checked 2 of those boxes with the airport and the Coast Guard station out there.
And I realize it's getting late, but we're excited about this. Bear with me. This is a really good business model. I mean, the CC was asking for us to demonstrate that this would really be a business model. And the reason is that Venn diagram there, thanks to Dave Carter. Critical facilities obviously need resilience because we're entering a time on Earth when storms are much more common, natural disasters are much more common, you know, Superstorm Sandy, Hurricane Harvey, etc. And so resilience is an important issue, and people are willing to pay for resilience. Meanwhile, there are many community choice aggregation programs that are happening in the state. PG&E estimates in, I don't remember, what was it, 10 years? I don't know, that 80% of their customers would be community choice aggregators or members of community choice aggregation programs. And those kind of programs are just like the one here. They're trying to provide renewable energy, local renewable energy for their customers. And then the investor-owned utilities like PG&E are really interested in this because they see it as the future of the grid. And these issues that I've talked about are issues that they know they're going to have to work out. And they actually have a companion EPIC program that is going to dovetail with this one to try to start working these things out on a system-wide basis for that utility. And one more slide to say thank you. These are the people that worked on the project. They did a great job. You know, they won international awards. And thank you to all of them. Three of the people that, and you saw pictures of Pramod and Jake, 3 of the people were grad students. So this was the grist for their graduate student work, which was also a wonderful thing. And
I would just add that most of our projects in the sustainability area have some degree of student participation. So many of our projects, including the microgrid, had student feasibility studies as their groundwork. And in many cases, like this one, students have different roles throughout even the project implementation period. It is consistently the funnest part, the most enjoyable part of our work to have students come out to the Rancheria and really study in place, really do field study where they can look at what's happening on the ground. They can wander around a real solar array, and we can wander around a real Tesla battery, and They can get in there and help us solve these problems, and they really have helped us solve these climate problems, these energy problems, these resilience problems that we have. Humboldt State University, the students here, and especially the engineering students, have made an incredible difference. And we don't do a good enough job of it, but I like to take this opportunity to say thank you to all of them, because it really keeps us motivating, and really we need more people doing this work. So thank you.
Thank you. Thanks for your patience. Questions? Larry?
What percent of your energy do you generate?
That's a good question. It was, do you guys remember? It was, Jim, do you remember from the final report? Yeah, about 20.
What was the question?
What percent of their total or their electricity, I guess you mean? Yeah, about 20% is the answer. Larry?
I want to preface my questions by saying I think this is really remarkable. I'm really glad this is happening, and this is a great demonstration project for the whole country. So I want to preface that. With that,
I'm sensing a but.
Question. One is a softball, and one is hardball. The softball question is, did you need any county permits for any of this? And if you had required it, how much longer would it have taken?
So it's a great question. We did not need county permits because it's on federal trust land, so it's federal land. It's subject.
Would it have doubled the time, would you say?
You know, Larry, I don't know because I haven't gone through a county process. But I'll add that we did have to go through a parallel CEQA process because it was state funding. So, but it was a solar array and a battery. So the state CEQA process was worried about, and rightly so, what they call off-reservation impacts. Are we going to create runoff from the site during construction? You know, we need to use best management practices for that. Is it going to create any sort of a viewshed issue or impact drivers on 299? All of those things were addressed in a parallel CEQA process that was done by the CEC, but which mirrored the tribe's environmental review, which is done by the Tribal Government Environmental Programs Division. So they had a finding of no significant impact. The state CEQA took that document and incorporated it in and found a negative declaration. So the fact it would have no impacts. Now, we did follow the standard state CEQA public comment period and all of those timelines. And we did that, I mean, we pushed the process, you know, we pushed it, but it would have been longer had there been public outcry against it. There's no doubt. But as far as the county, I don't know about those crossovers, but.
I do. So for the airport project, the county has already started the CEQA process. In fact, we would not have gotten the $5 million, well, we haven't gotten it yet, but we wouldn't have gotten the $5 million from the state if the CEQA process wasn't already initiated. So the CEQA process, and it's going to be a mitigated negative declaration, and it's already up for review, and it should be in place well before we get a contract from the CEC. I mean, probably the biggest issue at the airport was if there are any anthropological, cultural issues, like Indian artifacts or burials or things like that. And evidently there aren't. Oh, there's a rare plant, but it doesn't. It's at the airport, but it's not in this location.
Okay, I want to ask my hardball question.
Yeah.
And that is, according to your best estimates and according to my rough numbers, this would have had about a 30-year payback. If you had not received the grant, do you think the Rancheria would have done it for a 30-year payback?
They probably wouldn't have done it for 30, but they probably would have done it for something under that. I I mean, the lifetime of the system is about that. I mean, there's going to be some replacement investment and things like that. But that's sort of the positive component of working with a government as opposed to a tax investor or someone who's looking for a very quick payback. Developing energy infrastructure is not a quick payback business, as you well know. And so, yeah, they're used to those 10, 15, 20-year payback windows, and they have the appetite for it. But the thing to also remember is that this is a first of its kind.
Yeah, that's
so the costs of this would not be the same if we did it again tomorrow. I can't say how much less it would be, but it would be considerably less.
Yeah, and the 10th one is going to be a lot less.
Yeah.
You know,
So that kind of comparison is always good to do, but it is really apples and oranges when it comes to those kinds of things.
You know, Humboldt County is famous for installing energy systems that had very long paybacks in
Yeah.
the 80s and 90s.
We love it. Yeah.
Yeah, during you had a slide on the installation and commissioning phase of the project. What does RTDS stand for?
Oh, a real-time digital simulator. So as we said, it's a way, it had both hardware and computer simulated devices, and it's a way to assemble the system and test it and de-risk it.
Yeah.
In terms of managing the battery charge state, how is the decision-making process made between taking advantage of arbitrage opportunities and maintaining a minimum amount of resilience or backup power?
Well, there's a certain level of battery charge that it doesn't go below, so that there is always some backup power. But it's a I don't know, Dave, you want to respond to that? It's a complicated management system that tries to optimize performance and still take into account the fact that it has to be ready for an emergency. Is there any?
Yeah.
I mean, it's pretty much what you were saying, that you just maintain a minimum state charge in reserve for island events, and then anything above that is available to the optimization to try to minimize the cost. And then if the grid goes down when we're at minimum state charges, we have a small amount of runtime before the diesel has to come on to support the grid, depending on, and that the amount of time it can stand, it can stand on its own without the diesel coming on. Depends on the solar installation at the time and the loads. So then that load.
And it's going to get better with a
Yeah, with the
double-sized battery.
it'll
Yeah.
be,
Yeah.
rare that the diesel comes on at all.
Yeah. Carolyn, did you have one? And then
I'm interested in the mini microgrids.
yeah.
Sort of where is that project at this point? Maybe you could say a little bit more about how you envision it.
Sure.
Just when they had immediately I thought about, could you charge electric vehicles at the mini microgrid?
Yes. So we already have electric vehicle stations out at the Rancheria now. We have 2 of them with 4 ports. So if you guys have electric vehicles, come on out and see us. They're right by the tribal office. That is part of the design for this, is to incorporate electric vehicle charging. So it's going to be, again, as I said, solar on the canopy, about 60 kilowatts. A Tesla battery in the back, which is
It's 190 kilowatts, 170
I got it.
kilowatt hours.
yeah. So it's a pretty good size, but that comes down to what level of charging station you would put in there and how much power that would need, and we want to include that, and we've talked about it throughout. That might be phase 2, is to put more chargers in at the Rancheria, since we already have the ones there. And the ones we have there are connected to the microgrid. So we have that, so those will be
Right.
fine.
Say something about
Yeah.
the load management as
Yeah, I was going to
Yeah.
say that Lawrence Berkeley Lab is another partner in this mini microgrid. That's a good one. Right? And so it's the optimization is even more complex than it is in our microgrid, in the sense that it's trying to optimize not only the battery and the solar and the arbitrage, but it takes into account excuse me, the refrigeration equipment and the heating and ventilating and air conditioning equipment. So all of that stuff is in the optimization program, and it gets more and more complicated. But the idea is to have it operate very optimally and take advantage of, for example, the latency of soda that's in the cooling case that's cold and has a lot of thermal mass, and et cetera, et cetera.
So it's thermal energy storage.
Yeah, it's thermal energy storage as well as electrical energy storage. Yeah.
I think one of the things I find most interesting about the Solar Plus project is that it's being designed for this application across the state in a really large scale. So rather than dealing with a utility, which has broad impact, you're dealing with potentially 12,000 different owners that you want to convince of the power of this package. And it puts the tribe in a really interesting place as having been the pilot for this opportunity for communication with all of those people and thinking about the kinds of information passage that would happen there. And I'm just wondering if you guys have thought about what kind of educational opportunities in terms of not the technical aspects, but the cultural aspects, in particular things like food deserts, right? So when I think about why is resiliency relevant for convenience stores
Right.
all across the state, and you think about all these little pockets of food, it's the only place that it's captured, it seems like the tribe could have a really interesting role in propagating other cultural dynamic information. And I'm just wondering if that's
Potentially. I mean, I think that all of that can work as added context for why people might do this. But the main reason is the same reasons really that underpin the microgrid that we have now, which is, gas stations are going to be able to reduce and levelize their cost of energy. They're going to green the energy that they use. They're going to have more resilience so that when the power goes out or there's an earthquake or there's a landslide, they can get that fuel out of the ground, they can keep that food cold, and they can keep water and ice systems going. So there's all of those things. And we really do talk about in this project, we talked about it a lot, and we've done probably, as we said on one of the slides, 150 tours, I'm not kidding, probably more, of our existing microgrid out at the Rancheria. So we do a lot of outreach and education, and we like it best when people come look at it and see what's going on. We do talk about replication in the Solar Plus project a lot. It actually happens more frequently, I'm finding, than when we did the big microgrid, because we think there's more actual opportunity for immediate replication with the fuel station convenience store facility. So it's basically a facility scale microgrid, but important critical infrastructure.
And let me just add that the Rancheria and Jana in particular are fantastic at getting the word out and celebrating these systems, and they've done an excellent job.
Well, there's been a lot of interest in it, so it's been easy.
Well,
Dana?
we've got,
Thank you, Peter.
The Russians attack our utility grid, or microgrid.
you mean when they do?
They actually will, and here's why, if they're built right. So we are fortunate at the Rancheria to have a really excellent cybersecurity enabled IT staff. Our IT director teaches cybersecurity classes. If you can make sure that your microgrid system is cyber secure and you're disconnected from PG&E in such a way that people can't access that from the outside, then it does give you, it's not going to be perfect, but it will give you greater insulation from something, any kind of a hacking event, whatever that might be.
And
Probably.
the airport project, cybersecurity was part of a requirement for that. So people are thinking of that. Certainly it's going to be harder than it would be if you were just part of the regular grid.
Yeah. Dana and then Larry.
When you're setting up your tiers of loads so you can prioritize them in shipping events,
Yeah.
were the circuits all nicely organized?
No.
Sure.
This is the discussion we had early on, because in many ways that was one of the fun parts of the project, was to say, okay, what do we need to have on in a truly, like, we have to keep this place open and servicing people for health reasons and, you know, life, health, and safety reasons for a month. We're going to have to dial everything way back. And so how do we do that in stages? And then what are our critical pieces? And so, and really what we found with, of course, Randy's help was that, no, we had to do a lot of looking at how the system was set up. And when we talked early on, you know, we talked about microgrids. Like the military has microgrids of a certain flavor, but you know, as I understand it, you know, the military, these sites are set up that way. They're sort of designed that way from the beginning. Ours was certainly not designed that way from the beginning. So a lot of as an example, we didn't have an energy management system, which is kind of a subsystem that sits below the microgrid. We had to implement that as a part of this project, which...
That's another thing that Dave and Mark had to do.
That's right. But, you know, and as my father said about Boeing one time, you know, that brought us from sort of the 50s to the 70s in terms of our energy management. And then we vaulted forward into, you know, into this new space of microgrid with that subsystem. So it was great. But that's, yeah, it's been a challenge to figure out how to load shed and tile those pieces together so you can flip that one switch.
I want to
last
follow up on that
question.
very question. When you say flip that one switch, how much control do you have over the load shedding versus how much of it's automated?
Well,
It can be done all manually.
It can.
Yeah.
yeah. Actually, it is manual. It's all manual.
It is all manual, right?
But it's manual on a touch screen or a
Okay, so
computer
You
screen.
push a button on a computer.
You have some control to say this is going to last a week or this is going to last a couple hours, and then you can decide, you know, fairly early on how much to shed.
Yeah.
Right.
If
I mean,
we
if it's going to
know.
last 2 hours, you don't shed anything.
Well, you don't know if it's going to last 2 hours.
Well, yeah, but I mean, if there was a 9 earthquake, you would know.
That's true.
Yeah. So that's how we based it. We said, I'm forgetting, but we said sort of, we put different parameters on it. You know, less than 3 days, greater than 3 days was one of the bifurcating, you know. So we have different levels of things that we'll back off on. And then there's always the manual approach where you go flip the breaker. So we have the truly manual backup, and then we have this easy screen where you just go to one screen and you can choose your level of load shed and you can click on that button and it does it automatically.
Is that the energy management system, or is that?
It's the energy management system working in concert with the microgrid management system. Mm-hmm. Yeah.
Well, thank you.
One more?
One more?
One more?
Right.
We'll stay here all night.
How it's going to be good in an emergency? Like, is it earthquake safe? Like, is it going to withstand an earthquake?
Yeah. You know, it was built to our seismic risk zone. And I can never keep these things straight because they changed the Dana, you probably know this. They changed the classifications. It was, I think, either zone 1 or zone 4, and then they flipped it. Like, we're in the highest hazard seismic zone in the country. So, one of them. So, all of like the supports for the, and the cross braces for the solar array everything was designed for that seismic zone. And further, we talked with, you know, Randy Cox, the electrician, and, you know, people who laid the lines, and we talked about earthquake resilience throughout the project. Mm-hmm. So where we could, we thought about, okay, do we keep a little slack in those lines so that when things are moving around, they don't rip out of the the piece that they're connected to and that kind of thing. But as much as we can, everything on the Rancheria is designed to that seismic zone. So, and I think they do, I think it's between an 8 and a 9. Charles, you probably know this. It's between an 8 and, it's actually, I think it's like an 8.8 earthquake. So it's designed for a big one, which is good. Yeah. All right. Anything else?
Thank you.